Вы не могли посмотреть, она идет или нет? So today we will discuss automorphisms of K3 surfaces.
Видно только одну дозу.
Да? Сейчас.
Лево.
Странно. Только одну доску, да? А вот так?
Сейчас будет задержка.
Я поняла. Сейчас. Общем,
Скорее всего, на той доске видно, что видно на трансляции.
Да, это правда. Я пытаюсь, в общем, сейчас. Нужно вообще не 3 сделать. Сохранить. Сохранение позиции камеры. Sorry, I'm trying to... Ничего не поменялось, да, и в трансляции тоже?
Шаг по YouTube.
Но там...
Я сделала вообще 3.
Может, вот тут, да?
Как?
Камера.
О, только оно теперь совсем далеко. Отлично. Все, спасибо. So, automorphisms of K3 surfaces and automorphism. Of a complex K3 surface S. Then we can consider the corresponding isometry induced isometry, so that we obtain the following representation of an automorphism group of S. Automorphism S, two isometries of H2 SZ with respect to cup form. So from the Terrelli theorem that we discussed before, Terrelli theorem, we obtain the following things. So first of all, if we have a orthogonal transformation in the image of this representation, yes, then phi is in fact Hodge isometry. So Hodge isometry, and I will denote by phi c its complexification. So, oops. See? H2. So, so what we can say about this morphism? So first of all, so phi c preserves H to 0 bar in the complexified second cohomology. And from the Thorilli theorem, we know that the image of the Keller cone of S intersection with Keller cone of S is non-empty, so that for projective K3 surfaces we have the ample cone of S intersect the image of ample cone of S intersects ample cone of S in a non-empty way. Just because let me recall that ample cone is just integer points in the Keller cone. So if this is non-empty intersection, then this is non-empty intersection. And we discussed that Thorilli theorem also tells you that the corresponding morphism comes from the morphism of the corresponding K3 surfaces if and only if this condition holds. Okay? So now what I want to prove is that this map is in fact injective. So we used this last time. So let me formulate the corresponding theorem that an automorphism of a K3 surface S that acts trivially on the second cohomologies of S is identity. So we are going to prove this theorem. So first of all, let me recall some facts from theory of complex compact varieties. So for compact variety X, what we have? So an automorphism group, it's always a topological group, just because we can use compact open topology. So this lives inside holomorphic maps from X to X, and on holomorphic maps we have compact open topology. So this is a topological group always, but for a complex compact variety, this is in fact Lie group. Has a natural structure of a Lie group and for a Lie group we can consider the corresponding Lie algebra. That is just the tangent space in identity. Here identity is just identity automorphism, and the corresponding Lie algebra is isomorphic just to holomorphic vector fields on X. So holomorphic vector fields. So here we have a Lie bracket, of course, and the claim is that the corresponding Lie algebra is this is isomorphic to this Lie algebra. This is more or less follow from the fact that all holomorphic vector fields generate one-parameter transformation groups of X. And so this fact holds for all complex compact varieties. Okay? So this is always a Lie group, and holomorphic vector fields always are tangent spaces to identity in this Lie group. Okay? In complex setting. Even for non-smooth varieties. Maybe here I can say complex compact spaces, not just smooth varieties. Okay? But what we have for a K3 surface? For a K3 surface S, we know that its tangent bundle is isomorphic to its cotangent bundle. So holomorphic vector fields on S, this is the same thing as global sections of this. So this is trivial. Okay? So what does it mean? This means that for a K3 surface, automorphism group is discrete. Is a discrete group. Okay? And now let me prove this theorem. So we already know that automorphism is discrete group, and now we can use a theorem. Let me just formulate it of Fujiki. That is about compact Keller varieties. Let X be compact Keller variety. Let me consider its an automorphism of X that preserves some class in cohomology of scalar form on this variety. So this is a group that consists from automorphisms of S with the property that
X here.
Sorry. X. That preserves class of the Keller form. So yes, class. H2 C class of Keller form. Then the claim is that this group has only finite number of connected components. And also know that automorphism, that the connected component of identity lies inside this automorphism group that preserves a Keller class on X. Okay, and now how we can use this theorem in our setting. Suppose we have an automorphism that acts trivially on the second cohomologies of S. So in particular, the induced isometry preserves all Keller classes. In particular, this automorphism lies inside this group. So what?
Are we talking about S or X now?
Oh, about S, about K3 surface. Sorry. Yes. Suppose automorphism of a K3 surface S. So what we have? We have that this quotient from the Fujiki theorem, we know that this quotient is finite. And this is trivial. So automorphism of S is finite. And from this we obtain that our automorphism at some degree is just identity, right?
Yes.
Okay. And now suppose that this automorphism is not identity, so that n is greater to 1. To prove the theorem, we will analyze fixed points of this automorphism. So first of all, let me prove lemma that holds for all smooth compact surfaces. So suppose, and this is about this lemma is about neighborhood of a fixed point. Suppose that we have, suppose that X is a smooth, compact surface. And phi is an automorphism of finite order n, and suppose that X is a fixed point. Is a fixed point of this automorphism, then there exists local coordinates, one, the two of X, and n roots of unity, lambda 1 and lambda 2, such that locally our automorphisms in these local coordinates is very simple. This is just linear map. That acts diagonally with this n roots of unities. Okay. So locally, our automorphism in a is very around a fixed point is very simple. So how we can prove this? So first of all, we want to prove that we can linearize our automorphism. So suppose we consider some open subset of X, and we already consider it is a local map. And then there exists so what I want to prove that there exist local coordinates 1, 2, such that our automorphism is linear. So we just take a differential in 0 of this automorphism, and then apply it to these local coordinates. Okay. So we can linearize our automorphism around this point. So for this, consider the following function. This is the following thing. We just take some of differentials in 0 of our automorphism in degree minus I, and then apply it to automorphism in the degree I here from 1 to n. Let me recall that this is an automorphism of finite order, and order is n, so we can consider such a sum. Then, what is differential of G?
I'm sorry, what does the index minus I mean?
It means that we consider, so this is our automorphism, so it induces isomorphism between the tangent spaces. And this is a fixed point. So 0 maps to 0, And we consider the corresponding tangent spaces two-dimensional, and this is automorphism, so this is an isomorphism of tangent spaces. So this linear map is isomorphism. And we can consider its inverse. And we just apply the corresponding linear map to phi I y. Okay? So what is differential of G in zero? Sorry, it's very analytic, but when we are talking about automorphism of complex K3 surface, we're in an analytic situation. Okay, so what is differential in zero of this map? This is just sum. But maybe it's not very analytic, it's okay. And this is just an identity. So this means that we can use local coordinates Z1, Z2 from this function can be used as local coordinates around 0. And now if we apply G to the image of Y, then just by definition, this is d0 minus I plus I y from I to n, and this is
How did we get this?
what?
Okay, yes.
1 to n d0 I minus 1 minus n I plus 1 y, and this is just d0 y. So what does it mean? That with respect to these local coordinates, we have this equality. So in this local coordinate, our automorphism is linearizable. Okay? So with respect to our automorphism, and now since this is this differential is a linear map of finite order, just because our automorphism was of finite order. So it is diagonalizable. So after one more change of coordinates, we can obtain the desired form of our automorphism. Okay? Diagonalizable. Ладно, я не могу это писать.
Did we use here that it is a surface?
Nowhere. I think that maybe if we consider a smooth compact variety and an automorphism of finite order, then using these local coordinates, we can diagonalize it, and then using we can diagonalize it. Okay. So we obtain the statement. Also. Two. Okay, and now, and now we come back to our situation with a K3 surface. So it acts trivially on the second cohomologies. Hence, phi acts trivially on H to 0. Hence, for a symplectic form, omega on S, we have our automorphism preserve a symplectic form on S. So now let X be a fixed point. So what I'm going to prove, so we have this lemma that locally our automorphism acts around this point, acts in such a way, but I want to prove further that in our case, lambda 1 and lambda 2 are just inverse to each other. So why it's so? So suppose we have a fixed point. Then we have already proved that there are local coordinates such that we have such that our automorphism acts in a such way, but omega is just it's proportional to dz1 which dz2. So we obtain that in this situation lambda 1 and lambda 2 are just inverse to each other. And this is root of unity. Okay, so what we can obtain from this? So suppose we know that this root of unity is not identity just because we suppose that our automorphism is non-trivial. So we obtain from this that fixed points of our automorphism are isolated. So since our K3 surface is compact, we obtain that there is a finite number of fixed points. The number of fixed points that we will denote by n sigma is finite. Okay? So we obtain that locally our automorphism acts in such a way, right? But maybe. Acts in such a way so our fixed points are isolated. So since S is compact, there are a finite number of fixed points. And now I need two Lefschetz theorems about fixed points. So first theorem. Fixed point theorem. So suppose it's for differential manifolds, so it's from differential theorem from differential geometry. Suppose that X is a smooth compact differential manifold, and suppose we have an automorphism of X. Is an automorphism such that for all fixed points, X, determinant of the following map. So we consider identity as a corresponding. So we consider identity map on the tangent space to X minus the induced map. I don't know how to do that. The induced map of tangents. So X is a fixed point, so we consider the corresponding tangent map to our variety. It's induced by this automorphism map of tangent space, and we consider now we can consider determinant on such a difference, and we suppose that this is non-zero. Okay, and we denote by I +1 or -1 its sign. So sign of this determinant. Then first of all we claim that the number of fixed points is finite, but also we claim that if we take a sum of these signs, we sum over all fixed points of an automorphism, then we obtain the following alternating sum of traces of the restriction of the induced map on the cohomologies of X. Okay, so we have some. So we suppose something about the corresponding map of tangent spaces. Okay, and from this supposition we obtain that there are finite number of fixed points, and also we obtain that if we take the sum of the corresponding signs, then we obtain the alternating sum of traces of the corresponding of the induced map on the cohomologies. And now what we Yes, and now what we have in the case of a complex variety and bihomorphic automorphism. Is a complex variety and automorphism is bihomorphic. Then the corresponding signs are always 1. So this formula in our situation, in our case of trivial automorphism, of trivial automorphism of a K3 surface gives that the number of fixed points, so here we obtain just number of fixed points, is equal to what? What is this in our case of a K3 surface? Что, плохо все?
Ну, понять, как он наш ноль действует.
Ну а как он будет действовать наш ноль?
Тривиально,
So in our case, just because we know if our automorphism acts trivially on H2 of a K3 surface, then it acts trivially everywhere. This is just an exercise, just because we have already computed the corresponding Hodge time and so on. So we can obtain from this, just using the corresponding multiplication that respects the Hodge decomposition, that our automorphism acts trivially here. So this is just topological Euler characteristic of S, and this is 24. So we obtain first we obtain this formula, and now we will apply the second Lefschetz theorem, holomorphic.
I have a question here. So why signature is +1?
Here, just because in this case we take a complexification, yes? And if we take a complexification, it will decompose in eigenvalues +1, I, and -1 as before, as H0, as H10 and 01. Okay, so this will be conjugated, and we obtain that. So just because we hear this formula, it just take complexification of this, and from this we obtain that this is all real numbers and this is over complex numbers. It would just take complexification. Okay, and from this we obtain that sign should be 1 here. So theorem holomorphic Lefschetz fixed point theorem. So suppose that X is a complex, compact, smooth variety, and we have a p-holomorphic automorphism. Automorphism of X. Suppose the same supposition. suppose that for all fixed points x of this automorphism, determinant, the same determinant, is non-zero, then first the same, the number of fixed points is finite. Is finite. And the following sum identity determinant of ID minus is equal to minus 1g trace x or x. Okay? So in this case, if we summarize this over fixed points, then we will obtain an alternating sum of traces of the corresponding action on the cohomologies of x of the corresponding trivial line bundle. So in our case, this formula, okay, of is this automorphism of on S gives the following. So this determinant is just equal to this. We take sum over all fixed points. And here we obtain just an Euler characteristic of the trivial line bundle, and this is 2. Okay? But what we have, we know that this is the root of unity. So its model is equal to 1. So if we consider model of the difference, this is will be equal less or equal to 2. And this means that if we take the number of fixed points, so from this formula we obtain that the number of fixed points divided by 4 will be less or equal to 2. Yes, but before we obtain before we have proved that this is in fact 24, right? And this is a contradiction. Okay, I can repeat what just the idea of proof. So first of all, we reduce the claim. We suppose that we have an automorphism that acts trivially on cohomologies. So first, we have shown that this automorphism is of finite order, right? How we showed this, we used that the automorphism group of K3 surface is discrete. Then we use Fujiki theorem that tells you something about automorphism that fix some Kähler form, and of course our automorphism fix Kähler form. So from this we obtain that our automorphism is of finite order. Then we proved analytic lemma, a very easy one, that if we have an automorphism of finite order, and if we fix, yes, of course, first I should say that if we have an automorphism of finite order, then it's naturally first to investigate its fixed points, right? Because of course, fixed points will give us something in this case. So we proved a very easy analytical lemma that tells you that if we have an automorphism of finite order of a smooth compact surface, then locally it's linear, and if we have a fixed point of this automorphism, then around this fixed point, our automorphism is linearizable, and it acts just by multiplication by some roots of unity. Then we used that in our case, our automorphism should preserve a Keller form, and from this, not Keller, should preserve a symplectic form that is just some multiplication of dz, dz1, dz2, and from this we proved that in our case, our automorphism locally is multiplication by two inverse roots of unity. Yes, so we have proved that all fixed points are, or fixed points of our automorphisms are isolated. So since our surface is compact, we did use that there are a finite number of these fixed points. And then we used two Lefschetz theorem. So there are two famous Lefschetz theorem about fixed points. One is from differential word, and the second one is from holomorphic. And so just using these two theorems, we proved something about number of fixed points of our automorphism. So first we prove this using one formula, and using the second formula, we proved this. We have already computed this number before, just because locally our automorphism was linearizable, and it acts by multiplication by lambda x and lambda x inverse. Okay? And just using these two theorems, we obtain a contradiction from our supposition that our automorphism is non-trivial. So it should be trivial. So this more or less follow from two Lefschetz theorem about fixed points, and Fujiki theorem. Okay, and now what next? Yes, and now let me formulate corollary that holds true. Corollary. Holds for automorphism of K3 surfaces over an arbitrary algebraically closed field. Algebraically closed field. So because of course our when we proved our theorem, we used complex packing a lot. But let me formulate the result that holds in any characteristic. But we just suppose that our field is algebraically closed. With singular cohomologies, but we just need to replace singular cohomologies replaced by Vittal cohomologies. So here we should suppose that we have an automorphism of a K3 surface of finite order. Automorphism of finite order. So before we just proved that in our case our automorphism should be of finite order, and here we suppose that this is so. And assume that it acts identically on singular or on étale cohomology of X. Then from this we can prove that this is identity. I formulated this corollary just to show what we have in arbitrary characteristic. Okay? Okay. And now let me also now I came back to complex setting for a K3 surface. We can also consider for a projective K3 surface, we can consider also the induced map on Picard group. This map will be orthogonal with respect to the intersection form that we discussed before on this Picard group. Let me denote this map in such a way. But let me first note that this map isn't projective, injective. Injective. So, for example, consider the double covering of P2 ramified in a sextic. General sextic. Then Picard group in this case is what?
Z плюс Z.
Нет. Тут просто накрытие в секстике разлетенное. Проще. It's just one-dimensional. Okay? We don't consider the blow up. We just consider the double covering. So all now I know what kind of exercises I will add in X. All automorphism acts on the Picard group trivially. But of course, in this case, we have non-trivial automorphisms just because this is a double covering, so we can consider the corresponding involution. In fact, automorphism group.
Why automorphism cannot act by -1?
Just because, okay. Почему он не может действовать на минус единицу, right? Just because it should preserve ample bundle. It should preserve ampleness. Yes, so they act trivially. But automorphism of, unfortunately, we don't have time to prove a general statement about automorphism of K3 surface with one-dimensional Picard group. They are very easy. They are just or trivial or Z to Z, and in this case, this is Z to Z just because we have we don't have time to prove this, but in this case, we see that there is a non-trivial automorphism that is the corresponding involution. So here we have an involution of a double covering. Okay, so this map can't be injective. Okay, but we can say something. So preposition. That for an projective K3 surface as kernel is fine. So proof. Our K3 surface is projective, so there is the corresponding very ample line bundle, and we can consider the corresponding embedding into projective space. Very ample. So since we know that phi is in the kernel of this map, we know that phi fix our very ample line bundle. So phi acts linearly on its global sections. So our automorphism acts linearly on the corresponding projective space. So this means that our kernel is inside PGL n+1 C, and this is a closed algebraic affine subgroup. And since we know that kernel is discrete, we obtain the statement. Kernel S is discrete. So the statement follows. Okay?
How do we know it's discrete and
Just because our automorphism group, the whole automorphism group is discrete. We have already proved that automorphism group of any complex K3 surface is discrete.
complex projectable?
For all complex K3, in particular for projective. Even for non-projective, it's discrete. Just because this automorphism group is a Lie group in this case. It's a Lie group for all compact complex varieties. Okay? And we know that its tangent space is just holomorphic vector fields. And holomorphic vector fields on K3 surface are trivial. So its automorphism group is discrete. So our subgroup kernel is also discrete. And we embedded as a closed algebraic affine subgroup in a PGLN. So this is a closed affine subgroup in, and this is discrete, so this is finite. Okay?
В принципе, могли снова на теорему Фуджики сослаться, да?
Могли. Ну нет, но Фуджики оно все-таки про какую-то конкретную подгруппу. Ну могли бы, да. Могли бы. Okay, and now let me prove something about symplectic automorphisms. So, symplectic automorphism. So S is a K3, and now we choose a symplectic form on S, and suppose we have an automorphism of S. Automorphism. So we know that there exists a number, a complex number, such that the induced action on symplectic form is just multiplication of this symplectic form by this complex number, just from what we have seen before, because H20 part maps to H20 part, and this is one-dimensional, so our symplectic form, so the induced action on the corresponding symplectic form should be multiplication by some number. And now let me prove that its model is just identity. This is so we know that the intersection of H20 and 02 part, this is the corresponding integral. This is not just non-zero, but this is positive. And our automorphism should preserve intersection form. So this should be equal to the thing. And this is multiplication by these complex numbers. So we obtain that the model of this complex number should be 1. Okay? Just because this was the corresponding intersection form, right? And our automorphism should preserve intersection form. So we obtain this equality, and this is from definition, from our supposition, and this should be equal. So this has model 1. So we obtain a map from automorphism group of S to complex number of model 1, so to S1. And symplectic automorphism that we will denote in such a way is just the kernel of this map. So this is automorphism that preserve our symplectic form. Symplectic automorphism. Symplectic automorphism. And also anti-symplectic. This is when they don't preserve but just multiply it by -1. Okay, and symplectic automorphism preserve our symplectic form. Now for a non-projective K3 surfaces, this number can have infinite order. But for projective surface, K3 surface, we can formulate the following proposition. So if S is a projective K3 surface, then there exists a number that is less or equal to 66, such that image of our automorphism, of our map from automorphism group of S to S1 is the group of n roots of unity. So this number cannot be infinite, and it's restricted by such a not very big number, just 66. Okay? And now, to prove this statement, we will use the transcendental lattice that we didn't use for so long. So let me recall that. Как пишется transcendental? Transcendental lattice of S is just orthogonal to Picard group of S in the second cohomologies. So its rank is equal to 22 minus Picard rank of S. And now we see that signature of the induced intersection form is 220 rho S for projective S. Just because let me recall that H2SZ always have signature 319 and Picard group of S has rank. What is for a projective case resurface? What's rank of Picard group?
2 multi 20.
For projective.
20. Why not 20?
First of all, its rank is rho-x. Picard group. It can be trivial for a non-projective one. What's signature? No, not rank. What's signature of what's signature?
3 times hyperbole.
No.
Plus.
No.
1 and
From
this is Hodge index theorem.
yes, from Hodge index theorem, we know that if we have a projective surface, and if we have then orthogonal to an ample line bundle is negatively definite. Okay, so this is a Hodge index theorem that tells you that the signature of Picard group is this one. Okay, Hodge index theorem. Okay, so from this we obtain that signature of transcendental lattice is 220 minus rho at x. And now note that this transcendental lattice is invariant for all automorphisms of S. Just because Picard group is, of course, is invariant, and this is an orthogonal to Picard group. And now we can consider the corresponding real vector space, and we can consider here direct sum of 0, 2 to 0 part intersection with H2SR part. This is a two-dimensional real subspace that we will denote by VS. Two-dimensional real subspace. And note that the intersection form on this vector subspace is what? Intersection form on 2, 0, 0, 2 part is what can you say about intersection form of this? About signature.
It's like 0, 0, 1, 1.
It's positively definite, okay? On this part, our intersection form is just positively definite. So this 2 part comes from this, just because we have proved. So period domain is when we. So we have proved that our integral is positively definite for K3 surface. Okay. So this is positive. So we obtain that the intersection form on its orthogonal is negative. Okay, and now we have an automorphism of K3 surface. We see that preserves that the automorphism should preserve this two-dimensional real subspace and this and it's orthogonal, and acts on acts via orthogonal transformations. Sorry, I want to give the whole proof, and we started later, so I think it's okay. So and acts as an orthogonal transformations on these two real subspaces, and we know that here an intersection form is the intersection form is positive, and here is negative. So we obtain that all eigenvalues on Vs and on its orthogonals all has model 1, right? Just because it's important that is positive or negative on this subspaces. So just because this is an orthogonal transformations, so the corresponding intersection form is positive or negative, so it cannot be 0, so all eigenvalues should have model 1, right? Okay, but this means that all eigenvalues on transcendental lattice has model 1. And now what we have, so we know that our transformation our automorphism should preserve the lattice in this real vector space. So all eigenvalues of the induced map are roots of characteristic polynomial with integer coefficients. And now we can use so-called Kronekev's theorem. That tells you what? That tells you that if we have f, a mnemonic polynomial with integer coefficients whose complex roots are non-zero and lie in the unit disk, then the roots of this polynomial are roots of unity. So from Kronekev's theorem and this observation, we obtain that all eigenvalues, eigenvalues are roots of unity. Okay, so what we have proved so far, that if we have an automorphism of K3 surface, then all its eigenvalues are roots of unity. And what we wanted to prove? We wanted to prove that we wanted to prove something about its particular eigenvalue. So recall that we are trying to prove something about the number in S1 that is an eigenvalue of this automorphism on we see on 2-0 part. Okay, so we want to prove something about eigenvalue on our symplectic form. So we have already proved that is a root of unity. So we can suppose that this is a primitive root of unity. Now for primitive root of unity we can consider the corresponding как произносится циклотомический? Циклотомик polynomial. Ладно. Consider the corresponding mth cyclotomic. Надо было посмотреть. Cyclotomic polynomial of degree phi mu that is Euler torsion function. So let me recall that cyclotomic polynomial is just polynomial whose zeros are primitive m's roots of unity. So and this is a minimal polynomial of our root of unity over Q. So from this we obtain that this minimal polynomial should divides the characteristic polynomial f of the induced action on the transcendental lattice, right? Just because we have already shown that characteristic polynomial of the corresponding of action on the transcendental lattice has integer coefficients, just because it should preserve the corresponding integer lattice. So if we have a minimal polynomial of the corresponding root of unity, it should divide this polynomial, right? And what we obtain from this? From this we obtain that the degree, that is the Euler function of the corresponding polynomial, is less or equal to the degree of this polynomial. And what is the degree of this polynomial?
22 минус 4 кара.
22 minus, and this is less or equal to 21 just because this is non-trivial, because we suppose that S is projective, right? There is at least one M-line bundle. And from this we obtain that M should be less or equal to 66. Okay? And now what we have proved? We have proved that image of mu, that was the map from automorphism of S to S1, is inside a group of 66 factorial roots of unity. Yes. No, just because we proved that all its image are roots of unity of degree less or equal to 66. So, and if we, for example, obtain the root of unity of degree, a root of unity of degree 21 and 22, if we multiply them, then we obtain something bigger than 66. So first we obtain this, that this is a group of unity of 66 factorial. So this means that this lies in some, for some big N, roots of unity. But we have already proved that if we have a point in image of mu, then this is a root of unity of degree less or equal to 66. So from this, using above, we get that N should be less or equal to 66. Just because in before example, if we have a root of unity at 21 and 22 in the image, if we will multiply them, we obtain something bigger than 66, and we have already proved that we can't have such a point in our image. Okay? And this is the whole proof. It's okay?
Yes.
So that's all. Today I will send you an exam. Please send me its solution before next Friday. For those one who need to obtain a grading very soon. For those who don't need to obtain grading very soon, you can send me an exam letter. Maybe, может быть, я спрошу учебной части, если они разрешат поставить оценки позже, можете позже прислать. Все, спасибо. Thank you.
So next Friday we'll have no lecture or this
No,
is-
no, no,
this is
no,
all?
no, no. Next Friday I will check your